Hello again. It's been a while since you've seen me. I'm Patrick Parola. I want to extend another thank you to Professor Wilbrita Mayhew, who provided the videos for the first half of this course for us. Quite honestly, his videos are a slightly higher quality than what I was able to make. And that gave me a chance to put together some things for the second half of the class that are going to be a little bit better off for us. So let me get my head out of the way and let's see what we can do with this. Let's take a look at quadratic functions. There are a couple of different ways you can approach the idea of quadratic functions. My personal preference is to start with the squaring function. F of x equals x squared. You're familiar with the basic idea of the squaring function. If I sketch out some coordinate axes here, then we can plot some points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4 are commonly used points. Just evaluate that function at a couple of points. Plot those points on my coordinate axes. Do my best to draw the curve passing through those points, and we get a graph that looks something like this. This particular curve is called a parabola. There are several things we can do to play around with the parabola, but anything in this basic form is still called a parabola. And doing some things to this is exactly where I want to go next. There are three transformations on graphs that we've taken a look at. Changing the amplitude by multiplying by a coefficient in front, shifting to the left or to the right by adding or subtracting to the x value, and shifting vertically up and down by adding outside of the function. So g of x is a times some x minus h squared plus k. All right, so this function has an amplitude of a, or a stretch factor of a. It's also been shifted to the right by h. And shifted up by k. So if we have a parabola or a function given in this form, we can apply those kinds of transformations to it in order to figure out what the new graph is going to look like. So for example, if I'm looking at the function, say f of x is 1/2 times x minus 1 squared plus 2. I could, of course, just plug in a couple of points and find the general shape of the graph that way. But if I can transform the points that we had looked at before, that will make things a little bit easier for me. All right, so if I want x minus 1 to be 2, that means that x itself is -1. If I want x minus 1 to be -1, then x is 0, and then 1, 2, and 3. Then my y values, I want to multiply by 1/2 and then add 2. So 4 times 1/2 is 2, plus 2 is back to 4. 1 times 1/2 is 1/2, plus 2 is 2.5, 2.5. 0 times 1/2 is 0, plus 2 is 2. And then 1 times 1/2 plus 2 is still 2.5. 4 times 1/2 plus 2 is still 4. And by graphing these points, I can be sure that I'm still going to be looking at a clear picture of the parabola, and I'm still going to be able to identify where the symmetry of the graph happens to fall. So -1, 4 is right there. 0, 2.5 is somewhere in that general vicinity. 1, 2 is right here. 2, 2.5 is somewhere around that. And 3, 4 is right about there. All right, plotting those points gives me a curve that looks kind of sort of like that. And we again have a parabola just transformed over a little bit. Two features that I've kind of implicitly talked about here, but we haven't really looked at, are the axis of symmetry and the vertex. The vertex, wherever that point 0, 0 ends up moving to, is the place where the parabola turns around. When the parabola opens upwards, it will be the lowest point on the graph. And when the parabola opens downwards, as we'll see in the next example, it will end up being the highest point in the graph. Another feature of the vertex, if you draw the vertical line that passes through the vertex, the parabola is symmetric about that line. We call it the axis of symmetry. So when we're looking at a graph of a parabola, those are two things that we can pay attention to and make sure we're able to identify. Going back to my general form of the quadratic equation, g of x is a times x minus h squared plus k. If I take the transformations of this generic function, the point that was originally 0, 0, the vertex, is always going to be moved to the point hk. So the vertex of a parabola given in this form is always at the point hk. And the axis of symmetry is always the vertical line passing through this point. Vertical line is x equals, so in this case it's x equals h. So without having to do anything else, just looking at the equation, we can identify the vertex of the parabola at the point hk and the axis of symmetry, the line x equals h. With these ideas in mind, let's scroll down and take a look at one more example. This time, how about f of x is 2 minus 3x squared. Written not quite in the standard form, but we can rearrange the expression a little bit. It's negative 3 times x minus 0 squared plus 2. So my h in this case is 0, k is 2, and without doing any work whatsoever, I can state that the vertex is going to be at 0, 2, and that the axis of symmetry will be the y-axis, the line x equals 0. The other thing I want to notice here is that my amplitude is negative. Whenever you have a negative amplitude, it ends up mirroring the graph. So if I take a look at my key points, my vertex is at x equals 0. There's not really anything going on here. So since there's no transformation in the x direction, I know that I can take my same key points at negative 2, negative 1, 0, 1, and 2. Right? If x shifts, then I will want to move those key points with it. But really the idea is that your center point is going to give you your vertex, and then you want symmetry on either side of that. Right? I do know that when I plug in x equals 0, I'll get out y equals 2. I could choose to either simply evaluate the function at each of these points, which absolutely works, or I can play around with the idea of transformations to try to see where each of those points moves to. For the sake of time, let me quickly go through. And we're going to see that negative 1, negative 1, and negative 2, negative 10, along with positive 1, negative 1, and positive 2, negative 10, right? Axis of symmetry, we know that going up and going down from this point will get the same values. Sketch out some coordinate axes, and I've got some very negative numbers, so I'll make some very tall coordinate axes here. Plot my points in question. 0, 2, negative 1, negative 1, positive 1, negative 1, negative 2, negative 10, positive 2, negative 10. Play and connect the dots. Gives me a parabola that looks something kind of sort of like that. And again, before I scroll away here, as I said, the vertex when your parabola opens upward is always the lowest point on the parabola. When the parabola opens downward, the vertex is always the highest point. Similar type of problem that I'd like you to take a couple of minutes to play around with. G of x is 1 minus the quantity x plus 1 squared. Pause the video, take a few minutes, and graph this function on your own before you continue onward. I'll give you about 15 seconds. Again, pause the video. And when you come back, you should see the graph already established. So again, finding the vertex and axis of symmetry, set that vertex up as the central point in my table, take a few spots before and after equally spaced, plot those points, and that will give us the equation or the picture to go with that parabola. Up next, in general, a quadratic function is anything you can write as f of x equals ax squared plus bx plus c. By using the method of completing the square, whenever you have a function given to you in this form, you will be able to rearrange the function and make it look like the form that we had been studying so that you can identify the vertex and then graph from there. So, as a relatively straightforward example, if I look at the function f of x is x squared minus 4x plus 5. Remember the process of completing the square. I'll take my x squared and my minus 4x. Those are going to be important. I'll need those. And let's take that plus 5 and put it way over here out of the way. A perfect square trinomial is something in the form x plus h, the whole thing squared. And if you multiply that out, you get x squared plus 2 times h times x plus not x, we already have an x, plus h squared. So we play a matching game here. This minus 4 must play the role of the plus 2h. So I get that h is negative 2. Now, h squared is negative 2 squared, which is positive 4. And so I am going to add 4 to this function. But of course, I can't arbitrarily add 4 to a function. So I must immediately also subtract 4 from the function. By doing that, I have changed absolutely nothing except to take a very simple looking function and make it look kind of messy. Right, to get all of my doodles out of the way, let me just rewrite that f of x is x squared minus 4x plus 4 minus 4 plus 5. Now I want to group. The first 3 terms, the stuff we got from completing the square, goes together, and then the other stuff hangs out at the end. The whole point of completing the square is that you can factor that into a perfect square. It's always going to be x plus h. In this case, h is minus 2. So this is x minus 2 squared. And then minus 4 plus 5, simplifying that gives us plus 1. We've taken a function given in the general quadratic form, turned it into the function in the form that we had been studying. So now we can read this function, determine its the vertex of the parabola, the axis of symmetry, and go from there. In fact, for this particular case, the vertex is h, although I'm using the same letter for different things. Remember, in the general form of the parabola, we want that to be minus. So my vertex is at positive 2, positive 1, and my axis of symmetry is x equals 2. So setting up a couple of key points, put the vertex in the center, and then move to the left and right equal spaces. You can either follow transformation of graph, or you can simply evaluate the function at each of these points. No matter how you go about it, you should end up with, that's going to be when x is 0, f of x is 2. I'm sorry, when x is 1, f of x is 2. When x is 0, f of x is 5. And by symmetry, when x is 3, f of x is 2. And when x is 4, f of x is 5. So we've got a couple of points. We can sketch out some coordinate axes. We can plot those points. And we can play our game of connect the dots to get a parabola that looks something kind of like that. One more example, just to remind you of how to complete the square. Not 8. How about 11? 2x squared plus 6x minus 11. When there is a lead coefficient in front of the x squared, you have to do a little bit more work in completing the square. There are several different ways you can write the process out. They are mathematically equivalent. My personal preference is to immediately factor out that 2, leaving behind x squared plus 3x. And I'll leave plenty of space before I close the parentheses and subtract 11. Now looking just inside the parentheses, we have that our 2h is 3, which means that h is 3 halves. H squared is 3 halves squared, which is 9/4. So I want to add in 9/4 and then immediately subtract 9/4, because by adding and subtracting the same thing, we haven't done anything to the expression. It's an equivalent expression, just taken something that looked nice and turned it into something that looks hideous. Now the next trick is, remember that it's just this part that is the perfect square trinomial. So I'm going to take this 2 and distribute it over the stuff that I put in the blue parentheses and the stuff that's not in the blue parentheses. So I have that g of x is 2 times the stuff in the blue parentheses, x squared plus 3x plus 9/4, minus 2 times 9/4, which is 9/2, and then minus 11. Right? X squared plus 3x plus 9/4 is a perfect square trinomial. It's going to factor to x plus the thing we got up here, which was 3 halves. So this is x plus 3 halves squared. And then minus 9 halves minus 11. Right? Finding some common denominators there. 11 is the same thing as 22/2. And -9 and -22 together is -31. So x plus 3 halves squared minus 31/2. All right, we've got some fractions this time, but fractions don't really hurt anything. We can find our vertex, which is going to be at -3 halves. Again, remember, that's supposed to be subtraction in the standard form of the parabola. Because it's addition here, we need to make this guy negative. And then the y component will be -31/2. So we have our vertex. In exact form with exact fractions is generally best if you're trying to report the vertex on its own. If you are trying to graph it or work from there, dividing these out and calling it -1.5 and -15.5, probably going to make your life a little bit easier. All right, but we need that -1.5, -15.5 to be the center of our graph. And I guess we can do -2.5 and -3.5 moving to the left, and we can do -0.5 and +0.5 moving to the right. And when we do that, we will end up with, say, -13.5 and -7.5. And again, symmetry. So it'll be the same things going in the other direction. All right. Very negative. So let's draw some coordinate axes. Let's scroll the screen down a bit so we can draw some more coordinate axes. And so we've got -3.5, -7.5. which is right about there. We've got -2.5, -13.5, which is about there. -1.5, -15.5 is here. -1/2, -13.5 is here. And +1/2, -7.5 is right there. All right. So our picture of our parabola looks something kind of sort of mostly like that. So here is one more for you to take some time looking at. Pause the video now. Use completing the square to find the vertex. Use that to graph the parabola. If you restart the video in about 15 seconds, you'll see my solution. So pause the video and work on it for a bit first before that. All right. So again, working through completing the square, factoring, we can find the vertex at 1/2, 1/4, use that as symmetry, and find some points nearby, evaluate those points on the function, or use the tricks of transformations of graphs. Either way, you end up with these couple of points. Quadratic models. The idea here is we can use quadratic functions to model real-world situations and make predictions about the world. As you can see, I already have a situation written out, so let's dive right into it. An outfielder throws a baseball with an initial velocity of 24 meters per second at an angle of 25 degrees. The height of the ball, t seconds after the outfielder threw it, can be modeled as h of t equals -10 t squared plus 10.1 t plus 1.8. And we want to determine the maximum height of the ball. The first thing I want you to notice looking at this situation is that the function is given to us. We have to do no work to set up the function, which is convenient for a couple of reasons. Not the least of which is that the values of 24 meters per second and the angle of 25 degrees are already factored into this expression. We don't need to use them again, although they do give us some context clues. First of all, by reading the situation and seeing what is happening, we can see that we're dealing with a path that is going to start at an angle of 25 degrees, arc upward, and then fall back down. A nice trajectory that we can think of. The other thing that I want to notice is that my distances look like they're going to be measured in meters, and my times look like they are going to be measured in seconds, because I have that 24 meters per second given to us. But the numbers themselves are already taken into account in this model we don't need to use them again, and we can pretty well ignore all of this. Instead, we are focusing just on this function, and we are looking at an h-axis for height and a t-axis for time. Right? It is a quadratic model, t squared, t, and constant. So it is going to be a parabola. And since the lead coefficient is negative, it's going to be a parabola that opens downward, which is kind of exactly what we have as our rough sketch here. And whenever we have a parabola that opens downward, the maximum height of the parabola is the vertex of the parabola. So we can rearrange this problem as find the vertex of y equals negative 10x squared plus 10.1x plus 1.8. All right, this is not going to be pleasant. We have some ugly decimal numbers, but we can still go through this process. We'll factor out the negative 10. We will complete the square on x squared minus 1.01x. Right. Half of that is 0.505. And if we square 0.505, well, my handy calculator tells me that that's 0.255025. I'll round it to 0.255. So I add 0.255, and I also subtract 0.255, and I get y is negative 10 times x minus 0.505 squared, and then I'm going to have minus 10 times minus 0.255 is positive 2.55, and of course plus 1.8 as well. All right, if I add 2.55 plus 1.8, I'm going to get 4.35, and that gives me my vertex. Taking the place of the x coordinate in my original function was this idea of the time, and taking the place of the y coordinate in the original situation was the height. So reading this vertex and interpreting it in terms of the situation at hand, I'm going to get that after 0.505 seconds, the ball will reach a maximum height of 4.35 meters, right? Rounded approximately. because definitely those steps we took were not exact values. All right, so we can use this process when we have horribly ugly numbers. It does work. There is a shortcut method. If you take a look in the textbook or following along in Alex, you'll see that what they've done is complete the square in general, and they get a really hard to remember formula. Let's take a look at that next. So by completing the square on a generic looking function, we can get that the vertex is b over 2a and b squared minus 4ac over 4a as the y component. If you want to remember that and use that, that's perfectly fine. If you want to remember just this part and try to figure everything else out from there, that's actually also doable. And that's the process that I want to show you in the next example. All right. So in this situation, a farmer has 200 feet of fencing and wants to build 3 adjacent corrals of equal area. Here, a depiction to make sure you understand what's going on. We want to determine the dimensions, the length and width of this whole structure, which will maximize the area, and we want to calculate that area. So for this situation, we've got a couple of things going on. The first one is to notice that all told, there are 6 fences that we are building. There are 2, as I drew it, horizontal fences, each of length L. And then there are 4 vertical fences, each of length W. So the total amount of fencing we've used is 2L plus 4W. And I know that all told we have 200 feet of fencing. Rearranging this a little bit, I can divide both sides of the equation by 2. And I get that L is 100 minus 2W, which will be a useful substitution for us a little bit later on. The other thing that we need to pay attention to is the area of one of these corrals. This is a rectangle, and its width is clearly W. Its length not given here, but because we want these corrals to be of equal area, I can assume pretty conveniently that the space inside each corral is 1/3 L. So area is length, which in this case is 1/3 L, times width, which is W. And of course, we have this expression for L, so we'll throw that in as well. And we get that area is 1/3 times 100 minus 2W times W. All right, this is a horrible, ugly mess, but we can deal with it. Distributing a couple of places here, and we get that area is 100/3 times W minus 2/3 times W squared. Right, and I am going to leave that as the fractions 2/3 and 100/3. It will make life a little bit easier for me. One thing I know here is that this is a quadratic expression. It's quadratic in terms of W. It has a W and a W squared. So if I graphed area versus the various widths I could choose to use, I would get a parabola. And because the coefficient on W squared is negative, that means it's a parabola opening downward. And when you have a parabola opening downward, the vertex is the maximum position on that parabola. So if I rearrange just a little bit, I get that big A is negative 2/3 W squared plus 100/3 times W. And I'm going to even put in a plus 0. Then in my standard form, y equals ax squared plus bx plus c, I can see that a is negative 2/3, b is 100/3, and c is 0. We could continue to use completing the square here if need be, but there is a nicer approach. As we saw, we can complete the square in general, and then the vertex is going to be at the point HK, where H is B/2A. Sorry, negative B/2A. So I just plug in my points in question. A is 2/3, B is 100/3. Multiply top and bottom of the big fraction here by -3. Negative to get rid of the negative signs that are there, and 3 to get rid of the fractions in my fraction. And I get that the vertex occurs when my x coordinate, which is W in this case, is 25. So I need W to be 25. And then I can go and calculate both of the things that I'm looking at. I'll scroll up a little bit to remind you that we have this formula L equals 100 minus 2W. So W is 25 and L is 50. And finally, remind you that the area was 1/3 L times W, which is 1/3 times 50 times 25. Let's see, 50 times 25 is 1,250. And if I divide that by 3, I get something very close to 417. And my W was given in feet, so I guess I can go back and throw some units on. Those are in feet, and the area would be in square feet. All right, so a couple of different approaches that you can take to finding the vertex when the numbers start to get to be kind of ugly. The result is the same either way. And the key idea, once again, is that when you have a parabola that opens upward, the vertex is the minimum value of the function. And when you have a parabola that opens downward, the vertex is the maximum value of the function. So if you have a situation that is asking you about maximum or minimum, you can find the vertex in order to answer that question. Changing gears, I next want to go on to talk a little bit about inverse functions. Inverse functions follow up on an idea you've studied before of inverse operations. Subtraction we call the inverse of addition, because if you add something and then immediately subtract it, you end up having done nothing in a very messy way. Likewise, division is the inverse of multiplication, and the square root is the inverse of squaring, well, some of the time. In general, an inverse function is a function where if you take the function and its inverse, you have done nothing in a very messy way. Getting my head out of the way here. If I have some function that I operate on x, and I take some other function and evaluate that function at that point, then I have undone what originally happened in the function. So g of f of x is equal to x. And it should work no matter which order I do those two operations in. F of g of x should also leave me with just x. Being able to identify the inverse of a function is going to be very valuable. Of course, it lets us undo things. It will also let us play around with some ideas for problem solving. So, breaking down this idea, there are 3 specific tasks that we can study. The first one, which is a little bit more abstract, but certainly very important. How do we know when a function does or does not have an inverse at all? Then, once we can be comfortable deciding whether our function has an inverse or not, we can ask questions like, are these two functions that I know actually inverses of each other, or was it somehow fooling us? And then finally, just given an arbitrary function, are we able to find its inverse? In studying inverse functions, it becomes important to look at an idea called a one-to-one function. So thinking back to your first introduction to functions, we kind of think of functions as these ideas that take values, say an x here and a y there. And our rule takes that value of x and sends it to y. We call that rule something like f. To have an inverse function, then we have to have some other rule that will take my y value and send it back to my x value. We'll generally write that rule as an f with a superscript -1 that kind of looks like an exponent, but not quite. Now, there's one interesting property of functions that we have to be careful of. If you have a relation that takes a single x and sends it to multiple y's, then you have something that is not a function. But if you have a relation that takes multiple x values and sends them all to the same y value, then you still do have a function. But going backwards, your inverse going from y back to x is not a function. And so we need to have a very specifically designed function. Right? For any function, the idea is that you assign each x in the domain to exactly one y in the range. And if you assign multiple x's to the same y, that's not a big deal. If we have what's called a one-to-one function, in addition to that basic rule of all functions, each y in the range is assigned to exactly one x in the domain. Some very simple examples. F of x equals x. is 1 to 1. Name any value, you evaluate the function, and you're going to get to a specific point. Name any point you want to get to, and there's only one way to get there, by picking that thing itself. By comparison, g of x equals x squared is not 1 to 1, because g of 2 is 4, and g of negative 2 is also 4. If you can find two x values where when you evaluate you get to the same point, it is not 1 to 1. And again, keeping in mind this idea of an inverse function, we want some way of undoing the rule we just did. And if all we know is we executed some rule and we got from our starting point to 4, well, we've lost the information of did we start at positive 2 or did we start at negative 2? Because we lost that information, we cannot take an inverse. Right? So only 1 to 1 functions have inverses. There are a couple of more powerful analytic tools that will allow us to clearly identify whether a function is 1 to 1 or not. But a nice kind of visual aid that does always work if you can manage the graph is the horizontal line test. Just like the vertical line test for determining if a graph is a function or not, the horizontal line test tells us that if there are no horizontal lines that pass through the graph more than once, then we have a 1 to 1 function. On the other hand, if our graph has at least one horizontal line that passes through the graph more than once, then we can conclude that the graph is not 1 to 1. If we have a 1 to 1 function, we can find its inverse. If we do not have a 1 to 1 function, then we do not have a function where we can find an inverse. Sometimes that forces us to be a little bit creative. Right? G of x equals x squared is not 1 to 1. It does not have an inverse. We know that because if we graph g of x equals x squared, it fails the horizontal line test. Pretty apparently. Every single horizontal line that passes through this graph is going to have a positive and negative hit. So if we have a function that looks something like g of x equals x squared, and we need to be able to have an inverse of the function, sometimes we have to be a little bit creative. My favorite way of being creative is to restrict the domain. Generally speaking, we implicitly assume for any algebraic function that the domain of the function is any value of x for which we can evaluate the function. But that does not have to be the case. For example, I can define the function h of x is equal to x squared if x is greater than or equal to 0. If x is less than 0, this function is undefined. And because h of negative numbers is undefined, it allows us to bypass the problem that we had before. If I graph this function, I get a curve that looks like that. Again, to the left of the y-axis, there is nothing. The function is not defined. But having done that, this new curve does in fact pass the horizontal line test. This new curve is a one-to-one function. So this is one place where explicitly stating the domain of a function is very useful. Instead of dealing with the implicit domain we had before, we've now very carefully defined our domain. And we defined it in such a way that we forced ourselves to have a one-to-one function. So if inverse was important to us, then we are in good shape. All right. Identifying inverse functions, or as I prefer to think of it, verifying inverse functions. The idea here is that you are given two functions. F of x is equal to x squared if x is greater than or equal to 0. G of x is equal to the square root of x. Again, if x is greater than or equal to 0. Although we don't have to worry so much there because implicitly g of x is undefined if x is not greater than or equal to 0. Right? So if we're asked the question, are these functions inverses? Two functions are inverses if f of g of x is equal to x and g of f of x is equal to x. So to determine if these two functions are inverses of each other, we evaluate those two function compositions. F of g of x is f of the square root of x, which is the square root of x squared. Right? If x is greater than or equal to 0, again, is a restriction we have here, then we evaluate, and square root of x is the number you multiply times itself to get x. Squaring says multiply a number times itself. So if you multiply the number you multiply times itself to get x times itself, you get x. On the other side, g of f of x is g of x squared, which is the square root of x squared. And as you learn in basic algebra, when you study radicals, the square root of x squared is the absolute value of x. But we know that x is greater than or equal to 0. so the absolute value of x is just x. F of g of x is equal to x, g of f of x is equal to x. So I can conclude that f and g are inverse functions. Let's take a look at one more example. F of x is 1/3 x plus 2, and g of x is 3x minus 6. Some fairly straightforward linear functions in this case. But again, if we are asked if the functions are inverses, that means we want to evaluate f of g of x, which is f of 3x minus 6, which is 1/3 times 3x minus 6 plus 2. Distributing, 1/3 times 3x is x, 1/3 times minus 6 is minus 2, and minus 2 plus 2 is equal to x. But you do always have to check in both directions. G of f of x will be g of 1/3 x plus 2, which is 3 times 1/3 x plus 2 minus 6. Distributing, 3 times 1/3 times x is just x. 3 times plus 2 is plus 6. And then plus 6 and minus 6 cancel each other out, leaving us with x. So yes, f and g are inverses of each other in this case as well. Finding the inverse of a function. Remember, the idea of an inverse function, if we have y equals f of x, then the inverse is something we can establish on y to get x back as the result. And in fact, that's the way I tend to think about inverses. If I write my function as y equals f of x, and I solve for x, then the expression I have for y is the inverse. Although generally speaking, we always talk about a function and its inverse as of x. It's always f of x. So what I'm going to do is swap x for y, then solve for y. So if I'm looking at the function, f of x is 2x minus 7. And I'm asked to find f inverse of x. Well, I'll start by writing y equals f of x. So y equals 2x minus 7. And I'll swap my x and y. X equals 2y minus 7. And then I will solve this equation for y. Add 7 to both sides. Divide both sides of the equation by 2. I get that x plus 7 over 2 is the value of y, and that's exactly what f inverse is going to be. So f inverse of x is x plus 7 over 2. Yeah, that's all there is to it. We can double check our work by evaluating. F inverse of x, which would be 2 times x plus 7 over 2 minus 7, which is x plus 7 minus 7, which is x. And we can also check f inverse of f of x, which is going to be 2x minus 7 plus 7 over 2, which is 2x over 2, which is x. All right. We can check to make sure that the thing we found does in fact satisfy the properties of inverse if we need to. Strictly speaking, not necessary, but as you have seen many times in the past, that sort of reasoning is very often useful. All right. Something a little bit trickier. Let's take a look here at g of x is x minus 2 over x plus 2. And to find, this wouldn't be f inverse, it would be g inverse of x. We will employ the same strategy. Set y equal to g of x. Swap x and y. And solve for y. I guess in this case, I'm going to have to multiply both sides by y plus 2. And if I distribute there, I get xy plus 2x equals y minus 2. And I can subtract y and subtract 2x to get all my y's and all of my not y's together. So I have xy minus y, and I have negative 2 minus 2x. On the left-hand side, all of my terms have a single factor of y in it. So I can factor that y out and divide by the remaining x minus 1 to get that y is negative 2 minus 2x over x minus 1. Sure, there's a common factor of negative 1 or of negative 2 in that numerator. I could factor it out if I want to and call it negative 2 times x plus 1 over x minus 1. But I'm just as happy to leave it like that and get that g inverse of x is something like negative 2x minus 2 over x minus 1. All right. With that in mind, here's one for you to take a look at. H of x is 5 over 3 plus x. And I'd like you to find H inverse of x. Pause the video now. If you wait about 15 seconds, I will walk through this one on my own. So pause the video and try it, see what you get first. So employing the same strategy, set y equal h of x, and then swap my x and y. So I get x equals 5 over 3 plus y. Rearrange, multiply both sides by the denominator to clear out the fraction, distribute, get all of my y terms on one side. In this case, there's only one, so just divide by the thing being multiplied by that to get y by itself. Y is 5 minus 3x over x, and that is exactly the expression for h inverse. When you have situations where you have functions that have inverses, it can really make life a lot easier in a number of applications. So it's always something that we are looking out for. But for the sake of this video, I'm going to wrap up with that. Go ahead, get into Alex, go through some practice problems, see where you can get with that, and I'll see you in the next video.